Okay, so today we're going to be talking about homework 5, which focuses on the kernel support vector machine classifier and the multilayer perceptron. So we're going to come over here to the code first. We've got all of our numerous imports here. And then we've got some functions that we used. Tried to be a little more modest with the function explosion this time around. And okay, so the grid search complete, and now I guess we'll go ahead and do a train. We've got verbosity on so we can see what we're doing here. I have a smaller one set up, so actually that's good. So I had to set up the max iter to 2 million because it just took forever. And I, especially on the linear data, or the linear kernel, which is a point of confusion actually because, and I didn't look into it too deeply, but to figure out what the issue was. But so when this grid search is completed, then of course you get a CSV file, and inside that CSV file you've got all kinds of information. Well, you get a data frame, and then I saved it to a CSV file, and you get all kinds of information. One of them is the mean score time, mean fit time, and so looking at just the fit time, I charted it over here, and for the MLP, the fit time was, up to 100 seconds and whatnot. And then when you come up here to the KSVM for both the linear, so the linear is, these are, oh no, okay, so these are the fit times. So these, it's 16 seconds down to 11 seconds, and then for the RBF it's even shorter. But in my experience of it in person with my own clock, the total time that it took was a lot longer for the KSVM, especially before I was putting on the max iter and increasing the cache to 1000. There was a disparity there between the results of the grid search and what the results implied versus what I experienced, and it was especially the fit time that took the longest. Everything else didn't take hardly any time at all. So anyway, okay, so that is still going, it looks like. But then we've got our save to CSV, and well, you saw that it worked, so let's just go ahead and quit that and keep going. That's all it's probably saving new things here. Okay, and then there's one of the graphs working, there's another graph working, there's another graph working, and then this is for a different way of viewing. I didn't end up using it like this. I switched over to an older function that I had set up for homework 3 because I liked it better. Okay, so keep going, and that's just because I no longer have that as a variable in here. Okay, and then this is down where we're let's see, we're working on the probas here. making sure that the data is scaled. The SVC does not work with, when you have probability true for the proba, it does not work with unscaled data. You just get 0.2 for everything, for the probability for all classes. And then when you score it, you also just get just slightly over 0.2 accuracy. For scaled data, though, it works, and for the MLP, it works for it does the predict proba implicitly, and it works for both scaled and unscaled data. I don't know if they're perhaps set up a little differently, or if it's simply the algorithm. Okay, and then we've got our other fancy things here, and all that's of course going to take forever. So coming over here to the let's see what's being worked on here. Something in here. Okay, so coming over to the report, we're working on the MinSet data set, and it's a mini version of it with 10,000 samples and 5,000 testing samples, and it's balanced. For normalization, we looked at none and standard scalar, and one thing to note about standard scalar is that when you're doing the k-fold cross-validation, the scalar needs to happen within the fold and not when you import the data set and then run scalar and then do the k-fold cross-validation, because that leaks. Basically what you're doing is you are scaling all of the feature values based on the standard deviation and metrics that are used across the entire data set, which means that in a way each feature has information about the rest of the data set. So in order to maintain the isolation principle for k-fold cross-validation to work effectively, you need to do the scalar inside the folds. I didn't realize that, so it makes total sense, and I just overlooked it in other studies. I did know that at some point and had since forgotten it. So we looked at the algorithm families. Oh, and I'm already almost out of time. So we looked at the discriminative classifiers and the support vector machines in multi-class classification. And we looked at, I used the linear kernel and the RBF kernel. The linear kernel is sort of just redundant to linear KSVM, but it does result in slightly different results because of how it computes that in a kernel form. But I decided I just wanted to look at sort of the baseline and compare it to the nonlinear representations. So that was for my own benefit. And then also artificial neural networks are also discriminative classifiers, but they're one of their hallmark features or distinguishing features is that they use feature extraction rather than feature engineering, which feature engineering is when you give the features and you decide ahead of time, okay, this is what I think the model's going to look at and think about and use best. And feature extraction is when the neural network and the nodes extract the features about the data set that so you don't need the features ahead of time. It can find more abstract and strange and non-human familiar correlations within the data and use that to make predictions. So we looked specifically at the multilayer perceptron, which is sort of the foundation layer for the DNNs, and in some ways, in some of the ways they work in practice are fairly indistinguishable, especially when you use a DNN in a hybrid combination with a CNN or RNN as the final fully connected layer for classification. Here's all our formulas. I didn't get to quite all of them, but it's like I'm just building a collection. And then we use basic accuracy, number of predictions, number of correct over number of predictions. Learning patterns, these are sort of rules of thumb for each one. I don't have time to talk about hardly anything, so these are plots that are kind of looking at each configuration across a particular hyperparameter that was looked at. So you see how each configuration and all of its parameters held equal change with only this parameter changing, and this really reveals how different configurations have different responses to the change in those hyperparameter values. And so it's not all, the more and more hyperparameters you get, especially when you get to the MLPs and further on to the deep neural networks, you have a lot of hyperparameters that are sort of all affecting each other in different ways. Some of these reveal that, and some of these reveal very strong patterns. So standard scaling has a unanimous impact on all MLP models, with virtually every configuration performing better than on scaled data than unscaled data. Then you have other parameters that don't really show any difference between one change to the next. You see the differences along here because those are the different configurations, but they all show a general pattern of straight across between these value points at the very least. These dotted are the unscaled, and those are a little more irregular. And so on and so forth. So then down here we get to the really breaking down I sort of focus in on one key hyperparameter, such as C for KSM, and alpha for MLP. So and this is a zoomed in version for the really tiny alpha values, and then these are larger alpha values in a general pattern. Now we get down to the plots, the scatter plots that show the confidence comparison. Everything above the diagonal line is an MLP confident prediction, and everything below the diagonal line is an SVM confident prediction. And then the colors tell you whether or not they were right, regardless of their confidence. And then we finally look at misclassifications. In the correct, everybody's correct. You see some clear shapes and some clear patterns, but it's not really until you get to everybody got it wrong where it becomes crystal clear that these are difficult and why they're difficult. The difference between the SVM correct and the MLP correct might be that some of these these are sort of patternless, more patternless outfits. And so perhaps the SVM is focused more on basic shape patterns, whereas the MLP is sort of looking at more nuanced contextual information, such as patterns, and maybe patterns that are typical of one type of clothing article versus another, and which sort of represents more complicated correlations. And then finally we get down here to the best algorithm, and according to the scoreboard, KSVM RBF won for this particular study. However, MLP and neural networks certainly have their strengths, and this just may not have been. So I wouldn't necessarily say KSVM is better than MLP. I would just say that for this particular study, it won the race, and it just really is dependent on the study and the data set. Thank you.